What the gold foil experiment discovered. Um, and they have a charge of +1. The charge is actually 1.6 times 10 to the ninth coulomb, or 10 to the 19th coulombs. No, 1.6 times 10 to the negative 19th coulomb. Sorry. It's power of negative 19. However, we just set them relative to 1 because electrons also have a charge of -1. And protons and neutrons weigh 1 Dalton, while electrons weigh 5.486 times 10 to the -4th Daltons. And that's so negligible that we don't even count that, which is why we just say the weight is the protons plus the neutrons, because electrons will add this negligible amount, which nobody cares about. And when we get to atomic property, atomic number Z is the number of protons, as we see here in this nitrogen atom. We know now that any atom that is a nitrogen element, or any nitrogen element, has 7 protons in one atom. So one thing to note is that the protons will always equal the electrons in neutral atoms. The total number of protons plus neutrons is going to be the mass number. Technically, you can include electrons, but it's going to be negligible, of course. And the isotopes are same protons while differing in neutrons, which leads to higher mass numbers. All this means is that in nature, there's not going to be just one nitrogen isotope. There's going to be multiple, and the way to calculate the mass percent, you have to calculate the percent abundance times the mass um, to calculate the AMU they use in the periodic table. It's not complicated at all, and I can actually show you how to do it. So we can go to Sketchpad, and let's say we're trying to calculate. There's an element X, and there's an element Q, and what this means is that this is a second isotope. So let's say there's in the wild you find 90% of X. That means zero point 0.9 times the atomic weight. So let's designate this as 40, and let's designate this as 41 um, Daltons, or AMU, same thing. So what this means is, sorry, it's kind of small, but 0.9 times 40, and that means this is going to have a 10% abundance. It's going to be 0.1 times 41. And all we do is calculate the percent abundance times the mass, and then we add them all together. So 0.9 times 40 is equal to 36, and 0.1 times 41 is equal to 4.1. That means the atomic mass is going to be 40.1. That's all you need to know for 3.2.3.